Thank the organizers for the kind invitation. As I said, today I will talk about homological connectivity in random hypergraphs. So I will kind of introduce what kind of theories or theorems are known for classical random graphs, not hypergraph, but random graph. The first one I would like to talk the classical one we sometimes call Erdős-Rényi random graph. Because we are in Korea, I will somehow skip S and A so sometimes. And then, in order to introduce the homological connectivity, I will then talk about random simplicial complex. And then, as the title suggests, I will also talk about random hypergraphs. Then finally, I will discuss some extensions. So what is this Erdős-Rényi random graphs about? It was introduced in late 50s and 60s, and there were many fundamental results in this area. Before I talk anything about Erdős-Rényi random graphs, let me define the model. What do I mean by that? It's usually known as also GNP, the binomial random graph model, although this was not defined by Erdős-Rényi but Hilbert, but it's nowadays common to call this one as Erdős-Rényi random graph. What is it? It is a graph on n vertices. Throughout the talk, if I write this one, this is the set of integers 1 through n. So we have n vertices, and each pair of vertices is joined by an edge with a probability p, and independently of each other. Each pair of vertices is joined by an edge or line, if you want, with the probability p, independently of each other. Independent, too long, so independent. Is the definition clear? Yesterday there were introductions, and some of you were very young, and perhaps you might not be familiar with such a concept. So if there is a question about the model, you can now ask. So in other words, for each pair, we don't include an edge, of course, with the probability 1 minus p. It's the same thing. What has been studied in the very first paper in Erdős-Rényi is sort of the evolutionary point of view. What do I mean by that is that you consider p not just a constant, but function in n. And of course, we restrict ourselves to be the probability, which means 0 and 1, the rest is a function. As you can imagine, if the p is 0, this is the line is p is increasing, is 0, of course, there are no edges, so it's an empty graph. On the other hand, if p increases to 1, if p is 1, then of course we include an edge with for sure, so the graph is complete graph. The question is, if you increase or if you fix of p at some point, what kind of new properties might appear? Or what kind of properties disappear? Was one of the fundamental questions of the Erdős-Rényi when they introduced this model. There are many interesting properties here, but the one that I will discuss is the classical connectivity. So we call a graph is connected if all the vertices are pairwise connected by a path, sort of walk, then we call a graph is connected. What happens is that if the P is about log n over n. It's pretty small. I just rescale my eye, so indeed I had to draw here perhaps. Yeah? Log n over n, then something happens in view of the connectivity. What do I mean by that? If the probability p is slightly smaller than log n over n, then the graph is almost never connected. So if I look at here. On the other hand, if I'm here, if the probability p is a bit larger than log n over n, the graph is almost always connected. To describe it more precisely, let me introduce some notations. Throughout the talk, my n will be large. And often I will use this notation with high probability, means that the property holds with probability tending to 1 as n tends to infinity. N was the number of vertices. And then all the asymptotics and limits will be with respect to n. Yeah? As n, the number of vertices tends to infinity. So what Edosh and Rennie proved in their seminal paper is that the following. We let p be the function of this type over n, but not quite. We add some other bit. So where Cn is a function in n, what they show is the following. If Cn tends to negative infinity, just to make an example, yeah, it's not necessarily any function which tends to negative infinity, but for example, for you, just take minus log n. Then, with high probability, G and P is not connected. Yeah. On the other hand, if you take this function, yeah,
so P is a function of n.
Function of n like log n over n.
So P is associated in each edge, right?
It's each edge probability. For each edge, for each pair of vertices, we flip a coin with the probability p, namely log n over n. I add an edge with that probability. With probability 1 minus log n over n, we do not include the edge.
Why is it function of n? P is a function of n. It's a function of edge, right?
Edge probability, the function of edge, but each edge, potential edge. There are no edges a priori, there are endpoints. For each pair of vertices, say u and v, I flip a coin p. If it says add an edge with the probability p, then I add an edge.
P is a function of n. N is what is it?
N is the number of vertices n. N will be throughout the talk, number of vertices fixed. My universe, as I said, n is large, all the asymptotics are as n tends to infinity, but nevertheless you should think about n is a fixed large number, like million. Then when we say with high probability, we never talk about the limit object, but with probability 1 minus some function which tends to 0, like log n over n is a bad function, or 1 over n squared. So you have to imagine this notation, as I said. At the beginning it might be. So if I write it in this one with more proper manner, if you want to write it in a proper manner, this kind of probability, you have to write this one in this fashion. For all epsilon, there is an n 0, such that for all n which is larger than n, this n, say n 0, the probability that G and P is connected is larger than 1 minus epsilon. You have to understand in this manner, this notation, with high probability. Yeah, so, is this oh, thank you. Yeah, so you have to understand this with the high probability notation in this fashion. So as I said, each pair of vertices, we flip independent coin. This is very important. That's why GMP has been studied so much, because of the easy analysis. But then, If you come from different community, you do not want to have such a binomial model, but some other models, like the uniform model, fix the number of edges as well as the number of vertices. So if we want to have such one, so given a collections of graph with a fixed number of vertices and edges, you mix it, you select one uniformly random, meaning that with an equal probability, so 1 over the total number of them, then we call it uniform model. On the other hand, these two models can be equivalent if you choose the parameters in a proper way. So it's customary to work with it. If you are better with probability calculation, it's easy because of the independence. On the other hand, if you are very good at counting, then uniform model might be easier for you to work with. So anyway, this was the statement. On the other hand, if I take Cn tends to positive infinity, such as, it's just an example, it's not necessarily to be this time, Cn, now I change the sign, like plus log n, and then with high probability, G and P is connected. What it means is that just changing, just subtracting little number, which is much smaller than log n, we can just switch from disconnected graph to the connected graph. It's very sensitive around this value. So we give the name, inspired by physicists, such a property that G and P is connected, we say undergoes a phase transition at threshold we say in this manner. If you read papers in this area, often the titles will be of this type. Something, something, something undergoes a phase transition at certain threshold function. Threshold function is something where something is happening, as it written here, log n over n. So before, something doesn't appear. After that, some other property appears. So we will throughout the talk, I will refer to this one as threshold. Second thing is that after this paper, they wrote also several other papers, but many years later, people observed that if you look at this threshold for connectivity or connectedness, this is determined by a very simple property, namely isolated vertices. I'll explain what do I mean by that. This is done by Bolobash. And Thomasson, 85. What it means is that if you look at this evolutionary point of view of the graph, around at some point, when the probability is 1 over n, the graph consists of some component of linear size, say some constant times n. The constant can be determined, and there are several other components outside when the probability p is around 1 over n. It's a little bit larger than 1 over n indeed. Of course, in this case, the graph is disconnected. On the other hand, if we add more edges, because log n over n is much larger probability, if you reach that probability, during this time something will happen. What will happen is that the richer get richer. The larger become larger. Namely, if you throw in the edges with the larger probability, let's say, you throw in these edges first with this probability, later with 1 minus the probability, so that in the end we get as a union of these two probability, we get the original. So this, I will skip the details, you can make it rigorously. So if you throw in more edges, so that our edge probability becomes roughly log n over n, around this time what happens is that the two components will be more likely to be connected, rather than the small ones become connected, yeah, because I artificially add them, so I have to throw in more vertices. If I add more edges, it's more likely that the larger one get attached to the larger one, and so on. Of course, sometimes get the edges inside, get in, edit, and in the end, there will be only Poisson number of isolated vertices, and in the end, when this last isolated vertex become connected to the rest of the world, the graph becomes connected. This is so-called the heating time result. This is a beautiful result by Bolobash and Thomas. So it opened up kind of a new viewpoint of the random graph, not only the binomial model, but like as a process. I will not talk too much about it, but nevertheless, connectedness has a very strong relation to isolated vertices. Yeah, so a priori it's not clear. Is it clear that if the graph does contain isolated vertices, then graph is connected? But maybe the reverse is not true. But what their result says is indeed true. Instead of showing you the proof, it's just a lengthy paper, I will show you just the heuristic, how you get such a threshold. Yeah? 1 over n, if I want to write it here more precisely, you have to write in this fashion. C over n, where C is a constant which is larger than 1. In this case, it's a different C, yeah? This is the C bar. For any P, which is over the form C bar over n, where C is larger than 1, which means expected number of neighbors of each vertex is C. Why? Because for each vertex V, I have n minus 1 potential neighbors. Yeah, for each such potential neighbor, we do have neighbor with the probability P. So the number of neighbors of V is a binomial distribution with n minus 1 comma P. And if you look at the expectation of it, this is n minus 1 times P, but n is very large number, so we can just assume that this is n. P. And P is a C bar. C bar. So average degree is larger than 1. If you consider some correlated so-called branching process, what's going on is that start from a vertex. In each generation, you will see at least one child, because C1 is larger than 1. C bar is larger than 1. And this child will also have at least one child or children, and so on. It's very likely that the process will continue forever. It's very likely that the component will become large. This says this one. But I increase not only constant C, but much more is increasing functions, log n. So this was just 2. And now log n, because n is million, log million is what? Because we are very good at the binary numbers, 2 to do. So it will be 20. Thank you. He's a true computer scientist. Million, log million is 20. Yeah? It's much larger than C. Imagine n is really large number. The edge probability should be substantially larger to become connected. Yeah, this is all about. But about this Cn, just to forget about it, just log n over n is important. Yeah.
This 1 over n case is a special case of
no.
Cn goes minus infinity.
Yes and no. Depending on how you read this context. When we write such a thing, Cn tends to infinity in the second case or the first case, arbitrarily slowly, or up to it makes sense to talk about it. For example, if Cn is like minus 2 log n, probably P is negative. It doesn't make sense. So we take Cn to be an arbitrary function in n, which tends to negative infinity up to it makes sense. Cn tends to positive infinity also up to it makes sense. If I take n to be, Cn to be, let's say n, then probability p is larger than 1. It doesn't make sense. So we take arbitrary function up to it makes sense. So let me show you a heuristic. Then you might have some feeling. You might have some feeling why this number is appearing all the time. As I told you, what is important is this isolated vertices. It's very easy quantity to compute. Expected number of isolated vertices. If you know Bela Bolobash, he will say it's utterly trivial. But since we do have newcomers, it will not be utterly trivial. So we will do some computation. The same picture will hold. For each vertex, I have to look at using the linearity of expectation. What I will do is for each vertex, I will check. Yeah, so our vertex set is the integer set 1 through n. Probability, so using the linearity of expectation, probability that V is isolated. This probability that V is isolated, as I said, there are potentially n-1 neighbors, potentially. And I want to make it isolated, which means none of the edges should appear. And non-edge probability was 1 minus p. And these probabilities are independent, which means this probability is always 1 minus p, non-edge probability, times 1 minus p times ... up to n-1. On the other hand, these probabilities are all the same for any vertex, which means it's symmetric. Therefore, I can just add up how many of them are there. As I said, n is very large. P is almost log n over n, which means for large n, this quantity is roughly the same as 1 minus p to the n. Yeah, the n-1 you cannot see through million minus 1 from my glass. I do not recognize it. So it's roughly n. Then easy exercise from analysis tells me that n is the same as the exponent of log n, exp log scheme we often use. And also using some property or the Taylor expansion of the exponential function, you can also see that if p is very small, this function behaves roughly like exp of minus p times n. Yeah? That's a very easy lemma. You can prove at home. If p is very small, this behaves like e to the minus p when p is small. Small. So now, this is the expected number. What we can expect is if there are isolated vertices, we know that the graph is not connected. So what we are aiming for is when this value tends to 0, when this value not only tends to 0 but tends to infinity. So that we expect many isolated vertices. So, well, what do you think? This is value will tend to infinity, tends to 0, let's say, when p is equal to n over log n, or log n over n, then exp 0 is 1, right? So if p is about log n over n, something will happen. Yeah? But if I add a little bit more omega n will be any function, any positive function. If I add more, I'm doing minus log n plus omega n divided by n times n, so n disappears. In the end, minus omega n will survive. Exp of minus infinity is 0, tends to 0. On the other hand, if I take this suspected number log n over n, but a little bit less then because of minus Pn, this will be x plus omega n tends to infinity, x power infinity is infinity. You do expect that there will be a lot of isolated vertices, and using, just for the experts, Markov inequality, you can show the probability that there will be an isolated vertices tend to 0. On the other hand, here, it's not the case that you can just use Markov for something, but you have to use the Chebyshev, or as you wish, Chertonov, whatever you want, because in this case, all the things are independent random variable. You can show other inequalities or large deviation inequalities to show that what I show is true. There will be isolated vertices. So this is how you guess where the threshold should be. That's why I call it heuristic, not proof. Once you guess where things happen, then you have to prove what happens in the subcritical case. So by the way, this omega n, I just to change from Cn, just to confuse you. Then you have to prove first what happens when p is small, and then later you have to show what happens when p is large. And the proofs are not as simple as it sounds, but heuristic is usually gives the right threshold indeed. It's a very strong method. That's why the probabilistic method in combinatorics has been so popular, because just the first moment gives you usually the right threshold. So this was about the classical Erdős-Renyi graph. Of course, there are so many papers on the properties of random graph, and it has been extended in various models, random hypergraphs, inhomogeneous random graphs with a given degree sequence, small world networks, complex network, blah, blah. But in this talk, I will introduce the random simple initial complex, which was introduced by Lineal and Meshlam some 10 years ago. Motivation comes from more discrete geometry size, or algebraic topology, as this homological connectivity says. So let me introduce the model first. So you can digest while I prepare my blackboard what I have talked about up to now. So what is the model? What I want to talk about? It kind of opened up kind of new areas indeed. 10 years ago it was kind of a sensational model. If you want to become very famous, then you have to define very nice model. Then many people will jump into it and you become famous. Yeah, so random simple initial complex. Indeed, more precisely, I will talk about two-dimensional simple initial complex. I will denote it by delta 2 n comma p. So what is it? We start with, I will use some language that I don't know well, but that I will review. With full one-dimensional skeleton, on vertex at n. Yeah, what it means is, in other words, take all. There are people who are experts in algebraic topology and geometry, so if you have a question, you ask Andreas. One simple initial and 0 and 1 simple initial complex. Simplicity, sorry. And now comes the part. Yeah, we take all 0 and 1 simplicities. As I said, I will define all these terminologies because I had to refresh myself as well. And now comes, we let each triple of vertices, form an edge, form two simplex with the probability P independently. The picture might say more, so my universe will later be large, but to visualize it's easy to have just 4 vertices. Yeah, so I take full skeleton, so 0 and 1-dimensional simplices. So 4 vertices are there and all the edges are existing. Am I doing the correct thing? I don't know. Maybe yes. Yeah. Then each edge, so each triple, for example, this triple will form a 2 simplex with a probability P. This will exist as 2 simplex with a probability P, and the rest also independently. Is the model clear? Yeah. And what they show, before I show what it means, as I said, when I read this paper, it was during my visit to discrete geometry group in TU Berlin, and then I wanted to discuss this one with the group leader. But then he was busy with his own project, I was busy with my own project, and eventually I came back to this when I settled in Graz. So at the time I had to really refresh my rusty knowledge about the algebraic topology, which I learned here 20 years ago. So some reminder to me, some definitions. So I had to really look up, what does this mean, even Simplicial complex? I knew what it is. Pictorially, this was for me a Simplicial complex, but formal definition is the following. A family of, sorry for those who are expert in this field, but yesterday we learned that there are so many young people, a family of subsets of a set, subsets of a given set. So given a set S, a family X, of subsets of a set S is called Simplicial complex. If all singletons are included, and more importantly, it is downward closed. So I think since I came here several days ago, I was exclusively talking only in Korean. So my English has become kind of rusty as well. Downward closed. What that means is that if A is an element of this family and B is a subset of A, then B should be an element of X. Yeah? Imagine here. Yeah? So you can visualize it. And elements of X of size, given size, say K plus 1, is called K simplex. That wasn't not bad. It was an easy definition indeed. Yeah? But then, because I come from random graph theory, I do understand the graph theoretical terminology better. So we will refer, not only me, but many people refer to zero simplices, let's say, as vertices. Zero simplices are here, those. Yeah? Element of size 1. This one. Vertices. Whereas simplices of size 2, namely the pairs, these pairs, we call H. And 2 simplices is a face. If I made a mistake, you later correct with Andreas. Face, as I draw it here. We call it faces. And furthermore, there will be one other property about simplices. The set of vertices and edges form a very important graph, namely we call it as shadow graph. Shadow graph plays an important role in the homological complexity, so I just shadow graph. Finally comes the definition of homological connectivity. X is homologically connected if its zeroth and first homology group vanishes. But when you talk about the homology group, you might vaguely remember we have to talk about the coefficients, where the coefficients come. So in this case, in this talk, with mod 2 coefficients. Oops. Vanish. But also I learned from their paper, Lineal and Meshlam. I didn't talk about Lineal and Meshlam yet, but this model is defined by them. Indeed, for simple integer complex, homology group is the same as cohomology group. And now we have all these definitions, so now finally I can state the result of the Lineal and Meshlam. You can ask any question during my talk, yeah? Except some deep theorems from algebraic topology. Here we take P to be 2 log n, yeah? Twice larger than the connectivity threshold plus a Cn. Your Cn will be any function. So now it behaves similarly as before. If this function Cn is any function in n which tends to negative infinity, then with a high probability, two-dimensional random two-dimensional simple integer complex is not connected homologically. On the other hand, if Cn tends to positive infinity, then with high probability, delta 2np is homologically connected. This is twice as the Erdős-Rényi connectivity threshold. This suggests there's something easier heuristic is going on behind this scene, behind the scene. So let's understand what it means. Zeroth homology group vanishes. Zeroth homology group has to do with the shadow graph. If the shadow graph is connected, then zeroth homology group vanish. Shadow graph, by the way, of this definition, we said we take all vertices and edges. Namely, shadow graph is complete. By definition, in the Lineal and Meshlam model, the zeroth homology vanishes always. And therefore connected, which implies that zeroth homology group is the same as zeroth cohomology group. So I just write homology group. I learned this notation as well. Delta, I just abbreviate as delta, and F2, so mod 2 is a 0. Indeed, it's also cohomology, so it's 1. On the other hand, about the first homology group, it has to do with also the cohomology vanishes. If you play with the definition of these cocycles and coboundary, essentially it means that every one cocycle is one coboundary. Well, I think some of you maybe is tortured. Fortunately, the lineal and mesh lamp interpreted purely in graph theoretical terminology, namely the following. Threshold for Homological is the same as the threshold for the property that every edge in the original delta complex is contained in a face. For example, in this very simple example, for example, this edge is not contained in any face. So we call them isolated edge. Yeah, in a way, we were talking about in Erdős-Renyi graph, isolated vertices. In this simplex, instead of isolated vertex, we talk about isolated pairs of vertices, namely isolated edges. Yeah, it's not contained in any face. And now we can compute this one in a way easier way, namely the heuristic, why the threshold, this magic number appears, namely 2 log n over n. But on the other hand, if we work on random graphs a little bit, you might see this factor 2 is related with the disappearance of the last isolated edge, but nevertheless we will compute it. So I provide you again the heuristic for that, because as I said, today will be more heuristic argument than proofs. As before, we will just do the first moment, number of isolated, number of edges not contained in any face, contained in no face. So given an edge, say u and v, we have potentially n-2 neighbors, n-2 vertices, together with u and v may form a face. But we do not want to have any face. But this face is not a face with probability 1 minus p. The same thing. This is not a face with probability 1 minus p independently. So I do have, using this linearity of expectation once again, for pairs of UV from the element of the 2 element subsets, probability that UV is isolated, in this sense, it's not contained in no face, it contained in no face, is that I have potentially n-2 vertices together with u and v might form a face. But it doesn't happen with the probability 1 minus p. Independently, I have n-2 of them. And how many pairs are there? N choose 2 pairs. Up to constant term, this is n squared. As I said, our n is million, p is very small. It's roughly n1 minus p to the n. On the other hand, up to constant term, we do the same business. N square is the same as the exp of 2 log n. We have exercised this already. 1 minus p to the n is roughly p times n. Exp of p times n. Oops, 1 parenthesis. The same business is going on. This quantity becomes 0 when p is about 2 log n over n. So as before you play with this omega n. Therefore, if p is something, the number of such desired or non-desired edges tends to infinity or 0, depending on this omega n. The same business we will do. But you can see where the threshold comes, where this quantity is a 0, namely this expected number becomes a constant. Then you can guess the threshold. So this is p is 2 log n over n. Factor 2 appears because we are talking about the pairs being isolated, not a single vertex. You can imagine now, if you talk about sets or j sets, then factor j will appear here. If you are wishing, if you are talking about the higher dimensional simplicial complex, heuristically you can guess where the threshold should be. The j times something. This was, as I said, the breakthrough model. Not only the result, as I said, the model itself was kind of a sensational at the time, 10 years ago. If you come from a hypergraph community or the graph community, what kind of a, in a way, not natural, this is very natural, is that the shadow graph is always complete. Just using the minimal properties of the simplicial complex, what it says is that it should contain singletons of the base set, named the vertex z, and downward closed. Now we want to use this only this thing, two properties about simplicial complex, not that it does have full skeleton. So one natural way of defining is the simplicial complex arising from hypergraph. I will say it, but then I will state, yeah? What it means is that, by the way, three uniform hypergraph, perhaps I write it because of the people who are not familiar with the hypergraphs, although we heard it from Monday's first talk, so I will move into the third part. Random two-dimensional simplicial complex, which arise from random three uniform binomial hypergraph. First, what we do is we construct random three uniform hypergraph. First, construct three uniform hypergraph. What do I mean by that? We start with vertex at n. As it says, simplicial complex should contain singletons. I have 4 vertices as a running example. Then each triple of vertices forms an edge, forms a face with probability p independently. This is construction of this three uniform hypergraph. Indeed, random. This has been constructed in this line. Okay, each triple forms an edge with the probability p. As before, I used the same example. This forms a face. It's not a simplicial complex. I have to take the downward closure. Then take closure. It becomes clearer, meaning that we take only the edges only if they are contained in a face. Namely, as Edge said, I will take this, 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 but none of these because they are not contained in a face. It's another kind of a downside, two extreme cases of the possible random simplicial complex, namely only take the downward closure, linear mesh lump, take the full skeleton. That's a two extreme model. As the model suggests, the shadow graph is not anymore complete. It's not necessarily complete unless P is 1. Therefore, the zeroth homology group could also be complicated. Maybe disappears, vanishes, maybe not vanishes, maybe change over evolution of the P. Second thing, there are no isolated edge. Because by definition, we only take edges only if they are in faces. By definition, there are no isolated vertices. Therefore, this kind of observation will not valid. So this does not hold. Yeah, for our model, I just to change here, I introduce the notation. I will call it H3NP. Time is running, so I have to be quick. It's not anymore complete, therefore it's not 0. Homological is not the same because there are not such isolated edge by definition. So we have to find something new. As I said, so for simplicial complex, homology group is the same as cohomology group. What is a cohomology? First, cohomology vanishes if one cocycle is a coboundary. What it means, if you interpret, which means there exists a 0, 1 function on the edges. Yeah, you assign 0 or 1 on the edges in such a way that if you find a cycle in which the sum of the edge values is 1, then first cohomology group does not vanish. Is it true? So if I have 30 minutes more, I can do the exercises. You look at the kernel of the one cocycle map. You look at the image of the 0 cocycle map, and if they coincide, then you can show this one. Vanishing meaning that, as I said, the cycles, so every phase should be even. Blah, blah, blah. So as I said, essentially, one cohomology group vanishes if, as I said, you can find, so does not vanish, one first cohomology group does not vanish if you can find the 0, 1 functions on the edges so that our simplicial complex contains a cycle in which the sum of the edge values is odd, so 1, because we are doing mod 2 operation. Then the first cohomology group does not vanish. But what does that mean then in terms of a threshold? Indeed, like the heating time result of the Bolobash-Thomason, we can find a minimal obstruction, then it disappears. So it's the same as the threshold for the property that the last minimal obstruction I will call M disappears. Now I'm recycling this blackboard, so I have to erase it, the irrelevant part. And so we observe this one for that. Heuristic will come as well if you give me 2 more minutes. What is this minimum obstruction, M? As I said, what is important is this odd cycle. To have it, we have to create a phase, A, B, C, let's say. It has a property that A and C is contained in no other phase. There are no phase containing AC except that one. It's the single phase containing AC. The same is true. ABC is the only phase that contains A and B. There are no other phases containing A and B. For BC, I don't care. On top of it, we also insist that there is a path between A and B. Path. Why this is a minimum obstruction, or minimum I don't say, but obstruction, is that if you assign the value 1 and 1 on the edges here, and everywhere else 0, then every face is even, because these are the single faces having this 1 and 1 here. Everywhere else everything is 0. So each face is even. The value, the assignment, because we are talking about one cocycle. Sorry for that. It comes from the sums of the edge values. The faces values comes from the edge values. Because everywhere else is a 0. If you look at here, I also take here 0. 0, 0, 0, 0. But then the cycle consisting of PAB and this one will form an odd cycle. And it does not come from the vertex partition. Therefore, it is not co-boundary. Yes? So if you have such a assignment of the ones and zeros on this particular cycle, then you can show that it cannot come from the vertex partition. So you try to assign, I can have many edges. So if this is a 0, if it comes from the vertex partition, of course, the parity of this one should be the same, 0, 0, or 1, 1. 0, 0, or 1, 1. 0, 0, 1, 1, and because of this one, it cannot come from the vertex partition. Therefore, it is not a co-boundary, namely obstruction for the vanishing first cohomology. Yeah? If you come up with such an obstruction, now it's an easy calculation. As before, we will do heuristic, so before I state the theorem, I will do this one. Number of these obstructions. But you can show that this path exists in a very early stage. So when p is very small, like n to the minus 2, they appear already. So you can assume that such a path always exists, which means this is nearly the same as the counting the expected number, just using the conditional probability that such a thing exists. Namely, there is a single face ABC, and AC and B are not contained in no face. So, as before, we have a triple. Up to constant, we have n to the third choices. Face should appear with the probability P. For these two edges, none of the faces appear. For this face, n minus 2. For the other face, n minus 2. 2n minus 4. But because n is large, let's say roughly this one. If you do this x log business once again, you play with it. 3 log n plus log p minus 2pn. As I said, to find the threshold, it's enough to find a p so that this quantity becomes 0. When this becomes 0, when p is equal to what? Roughly, what do you say? You are playing. I have to make What? 3 log n over 2n perhaps? Yeah, but what should we do with this log p? I have to add up, right? But p, I know. P is roughly this much. So I interpolate. And so on and so on. You do and so on and so on and so on as you can wish. But then what it says is the log of n is then minus log n, which means this becomes 2 log n. So I can write here. Because of this one on the bottom, we learned that this is minus log n. So indeed this is 2 log n. Oh, surprisingly, it's not 3 log n. Plus, these constant terms disappear. What left is log n. The rest of the terms, you can see that this is big of what's constant. It's not very important. It's a smaller order term as this one. So I just roughly wrote this way. 2 times n. So this is not a nice way to write it. So I just to compare with the Erdős-Renyi result. Compared to the Erdős-Renyi result, at the beginning it looks like factor 3 over 2, but it was diluting. So indeed, it's roughly like Erdős-Renyi, but there are additional terms because we are talking about this isolated face. But I do not care about this one. So we are talking about non-existence of faces and existence of path, but nothing else. So this is suggested the threshold. Indeed, this is the threshold. So I have to state the theorem, and then I will finish. Sorry that I have now 0 minutes. 0 minute, but I think I will just state the result and then finish the talk. theorem by Oliver Cooley, postdoc of mine, Penny Haxel from Waterloo, myself, and Philip Supercell, postdoc of mine. We just submitted. It took more than 3 years to finish because to finding the minimum obstruction was not easy, first of all, because we are not familiar with first cohomology, but then proof itself was painful. So guessing tells us that it should be this one. But then we said the same business. We add up something or subtract something so that such an expectation blows up or tends to 0. So if, the same business, Cn tends to minus infinity, then with the high probability, our simple shell complex arising from hypergraph is not homologically connected. On the other hand, if Cn tends to positive infinity with a high probability, H3 and P is homologically connected. Thank you very much for your attention.